Let us work on checkpoint 6.62. They want us to use Stokes' theorem to calculate the surface integral, the flux of the curl of f ds, where f is the vector field z comma x comma y, and s is the surface shown below, and the boundary of the curve c is oriented clockwise. Now this is kind of a weird picture because I think it may be the textbook might have had the axes going in the wrong place. But in any case, using Stokes' theorem tells us that we can replace this flux of the curl integral. We can replace the flux of the curl ds with a line integral of the boundary of S of just the vector field itself dr. All right, so that means we want to identify the boundary. This looks like it's a closed surface, or it's not a closed surface, it's an open surface, and the boundary is right here in the opening on the YZ plane. So let's focus on that boundary in the YZ plane, and we have this circle. And again, the orientation seems to be a little bit messed up here with the graphics that they gave. I think the Y should be going the other way. In any case, pretending the X is pointing straight at us, and we're going to go in the clockwise direction. So the clockwise would be going down this way. The starting point doesn't matter when we're talking about going in the clockwise, or when we're looking at a closed curve, because starting point and ending point would be the same. So now we need to parameterize this. This is happening when x is equal to 0. So the parameterization for this would start off with x is equal to 0. Now the y and the z would have the sine and the cosine business happening. And if we look at this, and if we let the y component have the sine and the z component have the cosine, so let's put sine t and cosine t, and this has radius 1, so we can have this coefficient 1 in front. When t is equal to 0, we are at 0 in the y and 1 in for the z. And when t is equal to, we're going to go around to 2 pi, but when t is equal to like pi over 2, sine of pi over 2 is 1, so that would be 1 in the y direction, and 0, cosine of pi over 2 is 0, and that would be here. So it does look like we're going in a clockwise direction. To finish off the whole circle, we're going to go all the way to 2 pi. All right, so this is our parameterization. We will need to find its derivative to help us to do the line integral. So we need r prime of t, and that's still going to be 0. Derivative of sine is cosine. Derivative of cosine is negative sine. And that is your derivative. And to get us ready for the integral, the line integral, we would want the vector field evaluated at the parameterization. So the vector field is z in the first component, and our z is cosine px in the second component, which is 0, and y in the last component, which is sine t. Okay. All right, now our line integral. This is the boundary that we're looking at. This is the boundary of your vector field f dotted with dr will look like the integral from 0 to 1 of this vector field evaluated at the parameterization. And we're going to dot that with r prime. and that's it. So integral from 0 to 1, the dot product would be 0 plus 0 and minus sine squared t dt. All right, sine squared t, it's like a trig formula. I think you need to use a half angle formula, but I just ended up punching into the calculator, and so the integral from 0 to 2 pi, sorry, this should be 2 pi, turns out to be, the negative here will come out as a negative, and integral of sine squared from 0 to 2 pi will end up being pi. Okay, so that's your final result, and that is, instead of using the flux integral for the surface, which we don't even know, and I'd be afraid to parameterize, instead of doing that, we just focus on the boundary itself, and that's how we can use Stokes' theorem. All right, I hope that helps.